Hi, welcome to Mrs. Thompson's classroom today. We're going to continue our unit on polynomials. And so we've done linear functions, we did quadratic functions, and now we're going to talk about higher ordered polynomials. So today we're going to start by just talking about what a polynomial is, and we're going to look at some different things so that we can graph them. So we're going to talk about their end behavior and their zeros. And we will be learning what the intermediate value theorem is probably in our next video. So let's get started just by talking about what a polynomial is. So a polynomial is a function where we have positive whole number exponents. Okay, so the x will never be in the denominator. The variable, will never be underneath a radical sign. And so when we look at these, for example, in A, the exponents are a 5 and a 3. So this is a polynomial. In fact, because it has 3 terms, we would call it a trinomial. Okay? Its degree is the largest exponent. So it has degree of 5. Okay, so your degree is the largest exponent on the variable. Okay, all right, in part B, the exponent or the degree of x is 6. So this is a polynomial. In fact, it has 2 terms, so we would call it a binomial because it has 2 terms. And its degree would be 6. Okay. Now for C, we have a square root of x. This is like 2 times x to the 1/2. So 1/2 is not a whole number. So this one is not a polynomial. Okay. And the bottom one, we have x in the denominator. This would be the same thing as 4x to the negative 2. So this one is also not a polynomial. And I keep misspelling polynomial. Okay. Now, a couple of things about naming polynomials. You can name them by their degree. So if it is a first degree, then it is linear. If it is a second degree, then we call it a quadratic. If it's a third degree, we're going to call it a cubic. Fourth is a quartic. Okay? And above that, we're just going to stick with it is a 5th degree, 6th degree, and so on. They do have names for the larger ordered ones. You can also name it, as I said, by the number of terms. So monomial would be 1, bi would be 2, tri would be 3, or we just call it polynomial if it has many. Okay? All right, so some characteristics of the graphs of these functions. First of all, if it is a polynomial, the domain is always all reals. These functions are also continuous. Continuous, just in general, means we can draw it without picking up our pencil. Now, more specifically, that means they will never have any holes, they will never have any jumps or gaps, and they will never have any undefined places like vertical asymptotes. So they're all connected, okay? The end behavior is talking about where the arrows go. Because the domain is all reals, then we can have polynomials can go like this, or they can go in the same direction, but they will always go on forever. And so the end behavior is dealing with what the graph is doing to the far left or the far right. In other words, when x is approaching infinity or negative infinity. So we want to understand a little bit better about what that means. And so we can do what is called we can use what is called the leading coefficient test. Okay? So A sub n is the leading coefficient. In other words, it is the coefficient or the number in front of the largest degreed term. Okay? And if that is positive, then there are certain things that I can know. Okay? And this is the degree here. So if the degree is odd and the leading coefficient is positive, then the graph is going to go this direction. So in general, it will increase across the graph. Now, it may have as many little squiggles in the middle. We don't care. But we know the arrows will go this direction. Okay? If A is negative and the degree is odd, then it's going to go down across the function. And as x is really, really negative, it'll be a positive number. And as x is a really, really large positive number going to infinity, the function will go down. Now, when we have an even degree function, the ending values, the arrows, so to speak, the end behavior will be going the same direction. So if the leading coefficient is positive, the function will go upward. And if the leading coefficient is negative, the function will go down. Okay, so let's take a look at what this means and look at some examples. So on this function, first of all, the leading coefficient is, the leading coefficient is 2. That's greater than 0. The degree is 3, which is odd. Okay, so that means if I were to graph it, the end behavior is going to go like this. Okay, now how do we state that without just drawing the picture? Well, we're going to state that by using some arrow notation or some limit notation. So one way is just to say as x goes to infinity, in other words, as x gets huge, f of x also goes to infinity. So what I'm talking about here is x goes to the right, the function goes up. Okay? As x goes to negative infinity, so that's on the left side of the graph, f of x goes down. Okay, so this is just using arrow notation, but this is how we would describe what the graph is doing. Now, the other way to describe it is called limit notation. Okay? And so what we're going to do is we're going to say the limit of the function as x goes to infinity will equal infinity. And we would say the limit as x goes to negative infinity of the function is negative infinity. Okay? Limit is a very useful concept, and we use it a lot in calculus to describe what a function is approaching as x approaches some value. And when we're talking about end behavior, x is approaching an infinity, either a positive or a negative. Okay, so two different notations. Let's do another one. Now on this one, I don't have to multiply this out, but I do need to look at all the leading coefficients. So the leading coefficients of each piece is -1, 1, and 1. So that gives me a leading coefficient of -1, which is less than 0. Okay? I also need to multiply these leading terms, so -x times x squared times x cubed, to realize that my degree is 6, which is even. Okay? So if I have a negative leading coefficient and an even degree, then the function is going to go down. Okay? So on the left, the function is going down. And on the far right, the function is also going down. So the way I would describe the end behavior is to say as x goes to negative infinity, the function goes to negative infinity. So as x goes to the left, the function goes down. Okay, so in limit notation, x is going to negative infinity, so the function is going to negative infinity. Okay, as x goes to the right, to a positive infinity, the function is also going down to negative infinity. And so in limit notation, as x goes to a positive infinity, the function is still going down to a negative infinity. So this is going to be very useful when we're trying to graph our functions, because at least we know the direction that the graph is going, and that's a good starting place. Okay? All right, the next thing we want to know, other than the ending behavior, is where the zeros are. So the zeros are where the function equals 0. So these are also the x-intercepts. Okay? So one thing we want to remember is what's called the zero factor theorem, which tells us if a function equals 0, one of its factors has to equal 0. So in example 4, my function is already factored for me, so I can take so if I want to find its zeros, I can take each factor and set them equal to 0. Okay, now x squared minus 9 could be factored a little further, but it would also end up giving me x squared equals 9, so x is plus or minus 3. X plus 2 would tell me x is equal to negative 2, and x minus 1 will give me x equals 1. So I have 4 roots or zeros for this function. So once I know the ending behavior and I know where the roots are, now I can start connecting dots. Okay? All right, so let's do this one again. Now this one is not factored for me, so I'm going to have to factor. I noticed there are 4 terms, so I might want to start by grouping. So the first pieces have an x squared that I can pull out and leaves me with x minus 2. The second 2 terms I can pull a negative 2 out of, which will still give me x minus 2. So fully factored, I have x squared minus 2 times x minus 2. So if I set this equal to 0, then I can take each piece and set it equal to 0. So I get x squared equals 2, so x is plus or minus the square root of 2, and I get x equals 2. So I have 3 roots. So the question does arise, how many roots should I be able to find? Well, if you notice, this one had a degree of 3, and I found 3. Okay, so and when we had a degree of 4, we had 4. So the degree will help us find the number of zeros. So in this particular problem, I'm going to have 4 zeros. So let's see how that works. So I notice I can pull an x squared out of everything. And then this will factor further. The 6 is going to make it a 2 and a 3, and everything's positive, so plus 2 and plus 3. If I set this equal to 0, I get x squared equals 0. I get x plus 3 equals 0. And I get x plus 2 equals 0. So my roots end up being 0, negative 3, and negative 2. So I only have 3 in the list, and I said I thought I was going to get 4. Well, that's because the 0 here was squared, so this one right here occurs twice. What we call that is it has a multiplicity of 2. So if it occurs twice, and then I have a negative 3 and a negative 2, now I do have 4 altogether. One of them was just repetitive. Okay? All right. Now, so the multiplicity indicates how many times that factor appears in the polynomial. In other words, the exponent on the factor. So here we have, this one would tell me x equals 2 with a multiplicity of 3 because it happens 3 times. This factor would tell me x is negative 1 with a multiplicity of 2 because it occurs twice. And then finally, I have x equals negative 2 with a multiplicity of 1 because there's only one factor of x plus 2. So altogether, I have 3, 5, 6 roots because it was a degree of 3, 4, 5, 6 polynomial. Okay, now how does the multiplicity affect the graph? So let's put this all together here. So the first thing I want to do is I want to look at the leading coefficient and the degree to figure out the end behavior. That's where we're going to start. Okay, so the leading coefficient, if I multiply these things out, I notice I have a 2, I have a 1x, and then I have a 2x that is squared, okay? So that means I have actually 8x cubed. If I were to multiply this all out, that's what my leading coefficient would be. So the leading term. So the leading coefficient is 8, which is greater than 0. The degree is 3, which is odd. Okay? So the end behavior, as x goes to infinity, the function is going to go to infinity. And as x goes to negative, the function is going to go to negative infinity. So I'm going to go like this. Okay, so that's the first thing I do. Now we're going to find the roots. Okay, so I have x minus 1 equals 0 is one of my factors. And then I have 2x minus 5. So that'll get me x equals 5/2. But this one has a multiplicity of 2. Okay, so let's plot these things. X equals 1 would go here. And x equals 5/2, so let's see, that would be here. Okay. Now, the other thing I want to do, just to fill in some detail, would be to find a couple of more points. Okay. The first one I want to do is find the y-intercept. We found the x-intercept, so we want to find the y-intercept. That means x is 0. So I'll have 2 times 0 minus 1 times 0 minus 5 squared. So that's going to end up being at, let's see, that'll end up being at negative 50. So it's going to be, let's change my scale then and just say this is negative 10, negative 20, negative 30, and negative 40. So negative 50 is going to be down here. So my function is going to be coming from way down here, and it's going to come up till I hit that root. Okay? Now, I also might want to know what it's doing in between the two roots, so maybe I just plug in a 2. So I'll have 2 times 2 minus 1 and then 4 minus 5 squared. So that'll get me 2 times 1 squared, which is 2. So it's going to be, if I make this 10 and 20 and 30, it's just going to be right here above the grid. Okay, so I'm going to be coming like this. Okay, now let's get one more value bigger than 5/2. So maybe we plug in a 3. So I'll have 2 times 3 minus 1 times 6 minus 5 squared, which is still 2 times 1 times 1, which equals 2. So at 3, I'm still going to be just right here, and it's going to come back up. Okay? And so my end result looks like this. Now notice my scale is skewed because I changed the Y scaling and I didn't change the X. That is okay as long as we mark the graph and it's readable. The other thing to notice is what happened at these two roots. At X equals 1, it went straight through. Okay? But at X equals 5/2, it turned around. Okay, so if the multiplicity is odd, then it passes straight through. If the multiplicity of the root is even, then it becomes a turning point. So our next question is to figure out, well, how many turning points should a graph have? Okay. So let's see right here. We're going to skip the intermediate value theorem for just a minute. So the general rule is that each polynomial of degree n will have a maximum of n minus 1 turning points. Well, what does that mean? So this function here has a degree of 5. So the number of zeros is 5. The number of turning points is less than or equal to 4. Okay, 1 less than the degree that the function has. Okay, so when we graph our polynomials, the first thing we're going to do is we're going to use that leading coefficient test to determine the end behavior. Then we're going to find our x-intercepts or our roots to find their multiplicities. And then we'll find our y-intercept. And then we can look at symmetry and the number of turning points and just use a table to fill in the detail of the graph. Okay? So next time, we'll do a few more examples of sort of putting this all together, and we'll talk about what the intermediate value theorem tells me. In the meantime, if you're in class with me, you can start working on your worksheet for this lesson to get a little practice. And if you're not, maybe you can comment down below if you need some more help, or email me, contact me in the comments below, and I can get you to my website where there's worksheets that go along with these videos. So we will see you next time. Thanks for joining us in Mrs. Thompson's classroom.